For this problem, we find the points on the curve, and the curve is given by the function presented here, where the tangent line is horizontal. Now, what this can look like is something like this. All right, this is what it could look like, and what's going on here is we can, if I do have the graph, what I can do is I can just visualize, and I can see where the tangent line is horizontal. Remember, the slope of the tangent line is equal to the derivative. Also, horizontal lines have slope equal to 0. So, the slope is equal to the derivative, and horizontal tangent lines have slope equal to 0. So therefore, we are looking for places where the derivative is equal to 0. If we can find the x-coordinates where the derivative is equal to 0, we will find the places on the curve, the points, where the tangent line is horizontal. So the first thing we're going to do here is find the derivative. All right, that's our first step. So I am going to copy down the original function, which describes the curve. And it's at this place, well, along with many others, where I have to be careful to copy down correctly. So each step I might slow down and double check to make sure I copy that down properly. Now, when I take the derivative, I'm using the power rule. This is a sum of terms, each of which is a power of x. Except for the 1. Well, so the 1 is a constant. All right, I'm using the power rule. When I come to x cubed, I have 3x squared. How does that work? I bring the 3 to the front. That's x to the third power. The 3 is that power. I bring the 3 to the front, and then I subtract. 3 minus 1 is 2. I always subtract 1 from that. So from that power when I take the derivative. For x squared, I bring the 2 to the front, and then I have 2 minus 1 is 1. For x to the first power, well, the derivative is 1. You could actually use the power rule, but I'll just say the derivative of x is 1. And the derivative of a constant by itself is equal to 0. Notice that's not the same thing when I have 2x cubed and I take that derivative, I leave the constant alone. That's because it's not by itself. It's constant times x cubed. But a standalone constant right here, like, we have plus 1, you take the derivative, you get 0. Now, it is not really much work here to simplify. I'll do that. So we found a formula for the derivative. Step 2 is to then solve f prime of x equals 0. Now this might be sort of bad form according by some people because I don't see f anywhere in here. I'm going to use f because it's convenient to say y equals f of x. All right, so I can use this notation. But I'm going to solve this f prime of x equals 0. What I mean is I'm going to find all values of x that satisfy the equation, the derivative equals 0. Now, this leads to a problem where I factor. It's possible, definitely possible, that I could use the quadratic formula because this is a quadratic. All right, so, but I think I really think factoring will be easier for me. If I use the quadratic formula without just putting those numbers in, I'm going to get some large numbers and I can make errors because I pretty often make mistakes. Okay, factoring out 6 is what I have here. It's what I've shown here. And I can double check by using the distributive property and multiplying 6 back through to see that I get the line that's above. Now, the factoring can go really quickly if you see it. If you don't see it, then I would say you could use the quadratic formula for x squared plus x minus 2. It'll be a little easier because you factor out 6. But 2 is a prime number, so you're going to get 2 and 1. The only question is, since I have to have a positive and the negative multiplied to get negative 2, is it going to be minus 2 and plus 1, or the other way around? Well, if I have it the way I have it here, I'll have negative 2x plus x, which does not equal that middle term of positive x, so no. I mean, my method is a guess and check for the most part when I factor. I know there's tables that people write out. I just do it in my head or something like that, have an eraser ready. So this factorization is the one that gives us the answer that we want. Not that we want, it gives us the answer. Okay, and you can always double check. Put in 1 for x, and you'll see that in fact you get 0. Put in negative 2, and you see that you get 0. So now that seems like we're almost there, but this problem didn't just ask for the x value. It asks for the point, or the points. So to find the points, we need to, we need to get the y values. So we're gonna find the y values. I'm gonna just shorten to that, but what I mean is the y values that correspond to these x values. So, in a way, this is like, sort of the hardest part here, actually, because, it's all these little mistakes along the way. It's not the hardest part conceptually at all, right? It's just that if you are taking a test or something, or if it's going to get the correct number, then you have to be careful when you plug in these numbers. Now, don't put negative 2 into the derivative formula. We're putting it into the original function formula. And so we just have to be careful when we do this. I mean, the concept is pretty straightforward. It's the doing sometimes that can be problematic or lead to errors. But of course, more and more we have computers to do things. But if we don't put the right thing in the computer, that can be wrong also. Okay, I'll just group so I can have something that I think is a little easier to see. Okay, so apparently that gives 21. So that gives 1 point when x is negative 2, y is 21. And then I'll just go ahead and do f of 1. So what I'm doing here is I'm putting in these values, and I'm seeing and I'm putting them into the original function. It's a little cramped. A line? No. Maybe just put this down a little, skip a line. Okay. So I'll have 2, 1 to the 3rd power, plus 3, 1 squared, minus 12 times 1. This makes 2 plus 3 minus 12 plus 1. So that's equal to 5 minus 11, which is negative 6. Okay, so my answer is the points negative 2, 21, and 1, negative 6. So there's a few things I just wanted to talk about before I finish up. One of the things is that these problems don't necessarily go this fast or this precisely, except in this case it did because the derivative is a quadratic, and we can find the zeros of a quadratic. You can use the quadratic formula if you need to. And it's true, there might be no real zeros, but we can see that if we have a quadratic, if we use the quadratic formula, we'll have the square root of a negative. So we could actually, if that's the case, if there's no real zeros of this derivative, that would mean there's no places where the tangent line's horizontal. But anyway, my point is that we have a quadratic. If we took the derivative and we got a 5th degree polynomial, that would be that would have its own problems. But this is conveniently, because it's a problem out of the book, where we get a quadratic more done. Secondly, I wanted to say is that this is a very important topic in calculus, because what that shows us, where we have as we can see in the picture, is that if you have a tangent line which is horizontal, that may be a maximum value, maybe local, like this one, just in this little neighborhood, it's a maximum, or maybe a minimum. Finding maximum, not necessarily when the derivative is equal to 0, but it's a candidate for that. Why would we care about that? Well, we're interested when functions are at maximum, like the maximum temperature, or when it's at a minimum, the minimum cost. So that's an important application of calculus. Okay, so that's the end of this little video here.